Hey everybody, welcome back. This is still lecture number 16, video number 2. We're talking about the technology of hydropower. Okay, so the first thing we're going to talk about is, we have water and it's elevated some distance above some sink, which was the ocean. And so how are we going to extract energy from that water? And so the first thing we're going to talk about is a turbine, which is a device that we can use to extract energy from moving water. So let's say we have some inlet, some pipe, and we have some sort of valve controlling the flow of water. And then that pipe allows water to impinge on a device, a turbine. This is kind of an impeller. It's got these geometries such that when water comes through this pipe, some high-speed water, and hits these varying geometries, there's a lot of different types, we're not going to go over that, then it causes this thing to spin, right? So this is just like a wind turbine for water. So this is like a wind turbine. Sorry, my pen's freaking out a bit today. But for water. Okay, so water comes in through this pipe. It's at high velocity, so we have some high velocity water. And it impacts this impeller, causing it to spin. This is connected to a shaft, which is connected to a generator. And so this generator, the spinning shaft, is generating electricity, which then leaves the system. So looking at a control volume like this, we have energy entering through this part as kinetic energy. So the water is moving, it has speed, velocity, therefore it has kinetic energy. That kinetic energy causes rotational energy, which in turn generates electricity, which then leaves. So we're converting from kinetic to electrical energy. Okay, once that water hits, it has to go somewhere. Since it's losing a lot of its kinetic energy, which is being extracted, that water then leaves through some larger pipe, which we will call an outflow. And it falls down and leaves our system at some much smaller velocity because our kinetic energy has been extracted and turned into electrical energy. Okay, so it's as simple as that. This right here is the part we will call the turbine. And this is kind of the business end of a hydropower plant, right? This is the heart, the thing you need. But in order to get that, we have to answer a question of how do we get high velocity water? Right, so last lecture we just talked about head and potential energy, but suddenly we're talking about kinetic energy. How do we go from potential to kinetic? So that's where the next piece of technology comes in, the dam. All right, so I'm going to draw a little bit of a picture for you. So we have some water, and that water is being held up by some large barrier, a dam. We are all familiar with dams, I would imagine. A dam will look something like this. Okay, now here's the bottom of our reservoir, we'll call it, and near the bottom of the dam, is an intake where water is allowed to enter the dam at the bottom. This also has some sort of gate, we'll call it a control gate, and this device is able to move up or down. And here's the intake after the control gate. So you see we could control the flow of water, how much water we're letting through, just by moving this gate up or down. Very ancient technology, but it works. Okay, this water then flows through a long tube, which is called the penstock Don't ask me why it's called that. I literally have no idea. Okay, and then that water now enters the part we were just looking at, the turbine. So here's our turbine, which spins this shaft. You know, if you've been to like the Hoover Dam, you see there's kind of this building at the bottom of a dam. That's the generator plant. So here's the generator, here's the turbine. It's spinning this shaft, which is going up into this machinery that turns rotational energy into electrical energy. So we've got these electrical wires that are leaving our system. Okay, now this water, once it's gone through the turbine, is much slower, but still moving. It has to be moving, or we'd have a problem, right? We'd have stuck water. So the water is still flowing, and it comes to generally about the bottom of our reservoir, and the level of our water at the other end of the dam is always lower. So here's our water. It flows through the penstock, spins the turbine, exits out the, oh, I forgot to name that part. It exits out the outtake, and then is here in the downstream side of the dam. Okay, now you see, here's the height of our water, and here's the height of our water. That distance right there is the head of your dam. So by varying either how high the downstream side is or how high the upstream side is, you're changing the head of the dam. And we'll see why that matters here in a minute. Okay, but we still haven't answered the question, how are we getting this water moving with such high velocity? Are we just going to open this and suddenly water enters? Like, why are we expecting water to even flow through this at any appreciable rate of speed, right? Well, that's because on this side, way at the bottom, we have high pressure water. And then here at the outtake, we have low pressure water. So here we have pressurized water and not as pressurized water. And so we can expect the water to flow from the high pressure to the low pressure. Just like if you take a syringe and fill it with water and then push really hard while holding your finger on the tip, then you let it go, you've generated this high pressure, right? And you let it go, it's going to squirt out because water wants to be in the lowest pressure it can get to. But this still doesn't answer the question of, wait a second, how did we even get high pressure water? We were talking about potential energy. The water here at the top, that's got potential energy. Why are we taking the water out from the bottom, right? Shouldn't we be taking the water from the top where it's got the most potential energy? Why are we taking it out from here? All right, well, let's talk about water pressure. This is the true genius of a dam. It seems like such a simple technology. It's literally a rock you put in a river, but it does some cool things. So let's see. Here's our dam again, and we're just going to look at a column of water. So I'm going to draw it. Here's, oh dear, a little too high. So here's our water, and we're just kind of looking at a column, you understand. So just like we took a little section. So here's a fish, and here's a crazy octopus. Okay, so they're all in this column of water, which has some height, which we will call h. And so you can see the water here at the top has a lot of potential energy, right? It's high above the ground. The water near the bottom still has some potential energy, but not as much as the water up here. And then the water at the very bottom, you would think, has no potential energy, at least relative to the ground, because it's on the ground. So how is that even going to help us? Here's the rest of our dam. Well, let's talk about Bernoulli's equation. Okay, so the water at the top, right here, is at atmospheric pressure, which we'll call P atmospheric. But then as you start to go down this column of water, you'll notice that the water pressure increases because there's water on top of that water pushing on it, and water is heavy. So as you go down and your potential energy goes down, then your pressure as you go down increases. And these actually increase in a linear fashion. So we have Bernoulli's equation, which tells us that the pressure of a column of water, or really any chunk of water, plus, that turned out a little funny, plus 1/2 times the density times the velocity of that water squared, plus the density times the gravitational constant times the height is a constant. Okay, so these have units of pressure. Actually, see how pressure is by itself. And we don't have mgh like we talked about last time, but rho gh. But these all represent 3 different types of energy, right? So here we have potential energy. Here we have velocity, which means it's kinetic energy. And then here, pressure. Remember we talked about in class how pressure, units of kilopascals, actually have the same units as kilojoules per meter cubed. Pressure is just a unit of energy per unit volume. So it's stored energy as pressure. So these are just saying that there's kind of 3 ways you could have energy evident in your water. It's either pressure, or it's moving, so it has kinetic energy, or it's been raised some distance above a sink, and so it has potential energy. So you see, since our water is not moving in our column, we remove this, and we just know that the pressure plus our potential energy must always be constant, which means here at the top of our column of water, all of our energy is manifest as potential energy. Here at the bottom, we have no potential energy, but we have a lot of pressure. So no matter where we put this part of the dam that's going to take out the water, it doesn't matter, because eventually all of it will be turned into kinetic energy, because there will be some slight decrease here, more of a decrease there, more of a decrease there. So we're always going to drop to the same height to get to the turbine, and then we're always decreasing the pressure as we move along, because our outtake is exposed to water almost at atmospheric pressure. So say the outtake is about at atmospheric pressure. So no matter what, we're going to get some pressure and some velocity entering here, and it will be about the same no matter where we take out the water. Anyway, that was a long explanation for maybe a simple question, but I did want to answer, why do we put it near the bottom? Probably just because we have less pipe to go through, so it's less expensive, and we have less drag, because right as we move along these walls, the water is going to be experiencing drag, and that drag is going to steal some of our hard-earned potential energy and turn it into thermal energy. And we do not want thermal energy. It does nothing for us. Stay X'd. Okay. All right. So before we move on from the dam, let's talk about types of dams, and then we're going to talk about how we could model the energy we're going to get out from a hydroelectric plant. All right, so there's the kind of dam we just talked about, one you might see like the Hoover Dam, where you've got a solid piece of generally cement and steel, which we have used to block an entire river, right? So if we kind of look at this thing from above, here's a river, and we have put in the middle of the river this dam right here, and that dam is impounding the water. It is an impoundment dam. Okay, that's fairly common, especially used for very large power systems. If you're going to block an entire flow of a river, think of all of the energy you have in that river. The water might already be flowing, and since you have a lot of water, you could get a lot of head, right? If a lot of water is flowing, then that's going to easily fill up a very large lake, and the more head you have, the more power you get. We're going to talk about that. Okay, so that's an impoundment dam. There's actually a different type that's used more often than you think. You just don't notice them because they blend in really well, which is actually kind of nice. So this is a diversion dam. Let's say we've got some river and it runs along, and then it loses some elevation. Either it drops really rapidly like in a waterfall, or it just has some rapids that go down. So here we've got a river that's kind of wrapping around some hill and losing elevation as it does it. So what we're going to do is we're going to build a very small hole. We're just going to build a tunnel essentially that goes from the top of the hill to the bottom of the hill. And we're going to divert some of that water through this tunnel. And then at the bottom, we're going to have a little turbine that is being turned by this water and a small generator that is generating electricity, which we take away with electric wires. So this is a diversion, or often called a run-of-river system. These are much smaller, so usually a small power system. We'll talk about the advantage and disadvantage of each in our next video when we talk about statistics of dams. Okay, so these are the two different types. But let's move on to talk about how we can predict the amount of power we're going to get out of a hydroelectric system. So let's talk about the power equation. Now, we've done solar power, we've done wind power. Both of those were a little complicated. Well, dams, they're pretty easy. I'm going to tell you that right now. So we've got, let's draw our control volume. Here's some water. Here's our dam. Here's our turbine and our generator and some water. So we have water flowing through and electricity leaving. So let's make our system be the turbine and generator. So coming in, we have water that has some pressure and started at some height. So actually what we're going to do is we're going to make this our control volume. And we can say our water started there at some height at atmospheric pressure, and it ended here at some height also at atmospheric pressure. So here it's at atmospheric pressure because it's at the surface and it's at some height, and here our water is at atmospheric pressure and it's at some starting height, where our starting height is greater than our ending height, right? That is the head of our dam. So we can say that if we look at the energy in, the energy of the water entering is the energy of this piece of water right here, and the energy leaving is the same as the energy of that piece of water, assuming no losses. So really, the energy that's leaving as electricity is just going to be equal to the change in the potential energy of the water. So here's our energy leaving as electricity. Okay? And so from the last video, we learned that delta PE, or the change in potential energy, is as simple as the mass of the water. Say, let's pick a little packet of water here and a packet of water here. So the mass of that packet times the gravitational constant times the change in height, which again is the head of our dam. Okay, this is the maximum energy extracted. Right here, we didn't assume any losses. We said we had potential energy at the top, we had it at the bottom. The difference between those two potential energies was entirely generated as electricity. But that's not necessarily true. We're going to have drag moving through this pipe, and we'll have some electrical losses in the generator. But for now, we're just looking at maximum energy. Okay, now, since that is only a unit of energy in joules, we usually like to work in power, right? So we can quantify the performance of our dam. So we're going to determine this per unit time by dividing everything by delta T, or some unit of time. What that's going to do is turn our change in potential energy into a rate, which we indicate with a dot. So this is no longer the change in energy, but the change in energy per unit time, or power. So we're going to name that our max power coming out of our dam. That's what we'll call it. And that is now equal to the same equation, but we divided by delta T, so we're going to put that dot above M. This is now a mass flow rate. So instead of now looking just at a box and following that box through this dam and then ending the box outside of the dam, we're instead setting our control volume to be the dam itself. And we're tracking the mass flow rate of water entering and the mass flow rate of water leaving that control volume. So that's what this m dot represents, is the mass flow rate of water moving through our dam. Okay, but we don't really like to work in the mass flow rates when we're talking about liquids. Instead, we like to think about, instead of mass flow rates, just volume flow rates. You know, like gallons per second. You've heard these types of terms, but you've never heard of kilograms per second of water moving through a system. Maybe you have. It's because you're engineers. Okay, so P max now, we're going to rewrite this m dot in volume flow rate terms. And that is as simple as m dot, which is kilograms per second. And we want to get it as a volume flow rate. So let's write our volume flow rate, which we usually write as Q. That's meters cubed per second. So yeah, Q is always just Q. We think of as volume flow rate, not a dot. And then we need to get this, right? We need to convert somehow from meters cubed into kilograms. Well, that's as simple as putting the density, right? Kilograms per meters cubed. So m dot equals volume flow rate times density. So we're going to sub in this side of the equation for m dot, and we get Q times rho times the rest of the equation, G times delta H. All right. So that is the maximum power you can get out of a dam, accounting for the head of the dam. We see why head is important. Gravitational constant, that is a constant, not going to change. The density of water, generally the same. And the volume flow rate of water through our dam, which we control, just drawing our dam again, the side. Remember that gate? Well, changing the volume flow rate is as simple as moving that gate up or down. If we move it down and completely block the flow, then our Q will go to 0. If instead we completely remove that gate, then our Q will be the maximum volume flow rate. All right, now one more thing. We have to remember that this equation assumed no losses, when really we're going to have drag through this tunnel right here. We're going to have electrical losses. Our turbine does not operate perfectly efficiently. It doesn't convert all kinetic into potential energy. So we're just going to add an efficiency term. That's eta of our hydropower plant, times the rest of the equation remains the same. Okay, there it is. We're going to circle that in yellow and black. That is the power you can get out of a dam, understanding that this efficiency is a function of the volume flow rate as well as the head across the dam. A real dam, they're going to know exactly what that efficiency is, so they can get real-time data. For now, we can just assume that the efficiency of a plant is generally 85%. Okay. This next slide I actually kind of already talked about on the previous slide, but just to make sure we talk about it, let's talk about the functionality of a dam. Okay, so we've got some river coming in, and we have put a dam there. So it's formed a natural lake, which we call a reservoir. A reservoir is a body of water created by a dam. So here's our dam that we made. We've got some outlet, and then we've got water coming out. And so here is our body of water at some height above our lower body of water. Okay, so like we talked about, there's some internal tunnel here, right? And there is a gate. That gate is used to control the volume flow rate, which in turn is used to control P of the dam. So controlling a dam is as easy as moving that gate. Think about how great that is. A solar panel, a wind turbine. Remember how complicated it was to get exactly the right amount of power? A solar panel? It's really up to the sun. A wind turbine, generally up to the wind. You can do a little bit, but the wind's got to be blowing, and if it's blowing at a certain speed, you get out a certain amount of power. A dam, though, you've got all of this water waiting there in a reservoir. Think of this like a fuel tank. It's just got all of this energy stored as potential energy, manifest as water held above the sink. Right? This is water held above some height. So it's got some delta H above this point. And so you can open that gate all the way, get max power. You can close the gate and hold it off. So that's pretty great. We're going to talk about that in the next video, about why hydropower is so nice for deployability. But let's talk real quick about max flow rate. So this river has some flow rate, right? There's some amount of water always entering our reservoir, and then there's some amount of water always moving through our dam. Well, the flow rate of your river must be greater than or equal to the flow rate through your dam, or the reservoir height will decrease. And that is going to impact your delta H. If your reservoir height begins to decrease, your head goes down. And remember, on our last equation, head is just as important as flow rate. So these are things we got to be careful with, right? If you start taxing your reservoir too much, you're going to run out of fuel, or fuel that matters. The lower your head goes, as this gets smaller, then you can extract less power from your dam. Okay, well, that's it for the technology. Next, we're going to talk about some statistics of hydropower, a little bit history, and also the economics. And finally, some advantages and disadvantages, especially related to its impact on the natural world and how important it is as a renewable resource. All right, let's see you in the next video.